So welcome back, dear students. We will start the session for the Prestress concrete. For today's session, we will do the analysis of prestress and bending stresses. Before this, I would like to acknowledge the professor of IIT Kharagpur, Professor Sushant Chakraborty, for guiding me in this prestress concrete. I'll be using his notes mostly for this subject. So I'll share you the notes and you can use that. And the videos mainly will be concentrated from those notes. Okay. So you can see here analysis of prestress and bending stress. In prestress concrete, the steel is pre-elongated so as to avoid excessive lengthening under service loads. So which means the steel itself is pre-elongated. It is very much stretched so as to avoid the excessive lengthening under the service load. It won't further strain, or it won't undergo elongation under service load because it is already elongated, while the concrete is pre-compressed. It is compressed by a pre-compressing force so as to prevent cracks under the tensile stress. This we have discussed last class, which means the steel is elongated as well as the concrete is compressed. That's what happened. So as long as the tensile stress in concrete did not exceed the limit of modulus of rupture of the concrete, you know, the modulus of rupture of concrete is given as 7 root of FCK, that is a modulus of rupture of concrete. So if the concrete's modulus of rupture exceeds 0.7 root FCK, what happens? There will be crack formation, and as a result the reinforcement will be exposed, and as a result there can be corrosion. So as long as the tensile stress in concrete do not exceed the limit of modulus of rupture of concrete corresponding to the visible cracking of concrete, any change in the loading results in an effective change in the concrete only. That is, it is already elongated, so there will be effective change in concrete only unless there is tension coming. Only the reinforcement will take. Up to compression, the concrete will be taking. The sole function of the prestressing tendon being to impart and maintain the prestress on concrete. That is, we are providing this tendon only to impart the prestressing force, that is the compressive force, and that compressive force in the concrete will be fully utilized to take the load. That is, the changes in stress in steel is negligibly small. There is no change in stress in steel, that is very negligibly small. So in order to analyze, we are using three different concepts. That is, three different concepts may be employed to analyze such prestress concrete system. However, some basic assumptions are always made, like your basic assumptions that we make, that is, concrete is homogeneous, steel behaves elastically, the plane section remains plane before and after bending, that is, the strain distribution across the depth is linear. These assumptions are made, and based on that we are going to do the analysis of the prestress and bending stress in a beam. And there are three concepts, there are basically three methods to do the same analysis. The first one, or the first concept, is the prestressing to transform concrete into an elastic material. That is, first concept, we will assume the prestress or the concrete as an elastic material. In this concept, concrete is transformed from a brittle material into an elastic material. That is, we will assume that instead of the concrete to be a brittle material, we will assume it is an elastic material, and we will assume that there is no crack development. There is no crack developed in this structure. The prestressing system is in equilibrium due to the internal prestress and external loading. That is, at any circumstances, it will be in equilibrium due to the external load and the internal prestressing. The linear elastic theory allows results of stresses, strains, and even deflections to be superimposed due to different individual effects. That is, we are assuming it is elastic such that the linear elastic theory can be applied, and the linear elastic theory says that the stresses, different stresses happening, it can be accompanied, or we can divide those stresses and we can add at the end of the effect of those stresses. The strains can be added as well as the deflections can also be superimposed. Superimpose means we can divide this structure into different loading condition, we can divide it into different stress condition, we can analyze individually, and at last we can add that together. The second concept is prestress as a combination of high strength steel with concrete. So basically you have only the first concept to be studied, but still you need to understand the other two concepts also. So the prestressing as a combination of high strength steel with concrete. Here we are considering the prestress as a combination of very much high strength steel and very much high strength concrete, and as a result we will analyze the stresses or the forces being acting on those two materials. Here, the high tensile steel taking tension and high strength concrete taking compression forms a resisting couple, because these two forces, the high tensile force and high compressive force, forms a resisting couple against the externally applied load. You can assume that. That is, in order to resist the externally applied load, this tension in steel and this compression in high tension strength concrete will be used, and that will act against the externally applied load. But this it's very however its difference with ordinary reinforced concrete must be understood at the very beginning. That is, we need to understand the concepts, how it varies, how it behaves with difference to the ordinary reinforced concrete. The tendon, first of all, the tendon is not simply buried in concrete but pre-tensioned. Therefore, it will always be active in nature. That is, it is always under high tension. It's not resting simply, it's not sitting simply, it's always working throughout its service life. So it is always in tension, but pre-tension, therefore active in nature, and therefore no need to elongate further the full strength of this steel is developed. That is, it is active, it is under tension, and further there is no need of elongation to take the load, because it's always already in tension. So in order to attain the ultimate load, in case of RCC, it was once the ultimate load reaches, or its yield strength reaches, then only it will elongate, right? Then only it will elongate, or the strain, it will go for its ultimate strain. But here it's always in the active state. As a result, even after the application of the load also, means again after it reaches its ultimate strength also, it will be further, it won't be elongating, because it's always already elongated. Now, the surrounding concrete need not to crack to give the tendon to elongate to develop stress, which means it doesn't need to wait for its ultimate strength to elongate. Since the concrete section is uncracked, its full effective depth area can be utilized for resisting compression. This gives rise to the varying lever arm concept and pressure line. So this concept, that is, we'll assume it as a couple which will resist the external applied load. That is your second concept. Based on that also we can do the analysis of prestress and this one, that is your bending stress. The third one is little bit more complicated when it is going for a smaller structure, but it's very easy when it's very useful when it's going for a higher structure. That is prestressing to achieve load balancing. That is also called as load balancing concept. So this concept is to visualize prestressing primarily as the balancing of gravity, that is your self-weight, and the imposed load. The application requires replacing tendons with forces acting on the concrete along the span into free body diagrams. That is, at any section we'll take the section, we'll draw the free body diagram, and the externally applied load will be used for analyzing. The free body diagram of these two will be analyzed and the analysis will be carried out. This approach may appear unnecessarily very much hard for a simple cases, but in fact very effective for a complicated structure. It is very effective when we are going for a complicated structure, but for a small structure it is very hard, or it is very tedious job. So these are the three concepts, and mainly you need to focus on the first one, that is prestressing to transform concrete into an elastic material. So for that we'll go into this. You need to understand certain terms. That is, for the analysis purpose, the first one is the prestressing force. The prestressing force will call it as capital P, that is taken as compression as positive. Small e, that is the eccentricity of the prestressing force. The moment created due to this prestressing force, and E, that is Pm is equal to P into E, that is the moment. Area of the concrete member, that is the cross-sectional area of the member. I, the second moment of inertia of the cross-section about the center of the axis, the moment of inertia. Z suffix T and Z suffix B, that is the section modulus of the top and bottom fibers. FSUP and FINF, that is the prestress in concrete at top and bottom fiber. That is also, it is also called as FSUP is the top superior stress at the top superior fiber, and FINF will call it as stress at the inferior bottom, that is at the bottom. Okay, and YT and YB are the distance of the top and bottom fibers. I is the radius of gyration. So we are going to discuss this thing in detail. Before that, you need to understand the terms. That's it. You consider a simply supported beam like this. Here consider a simply supported beam like this. The centroid of this beam is over here. So if I am placing the tendons, suppose I am placing the tendons like this, exactly at the center I am placing tendons, and I am anchoring it, and I am doing all the pre-stressing force, which means the load will be acting like this. The P stressing force, capital P, will be acting like this, which means the cross-sectional area of this concrete is like this. The pre-stressing, the tendons you can see exactly at the midsection of this. You can see exactly at the midsection of this, and the pre-stressing force will be P that is acting over here. For a cross-section, this is A. Cross-section, this is A. So I can say for this cross-section, if I am drawing the stress diagram, that will be a compressive force throughout. A compressive force throughout. That is, we'll take the compressive force as plus positive, that is P by A will be here throughout, and there is no eccentricity, so there will not be a moment. Now the same case, what I am going to do is, I am going to shift this prestress somewhat, or I am going to provide some eccentricity from the neutral axis. So here, if I am drawing the same case, I am drawing neutral axis somewhere here, and now I am placing the tendons at an eccentricity E. At an eccentricity E, this term I am taking as E from the centroidal axis. So the force will be acting, the pre-stressing force capital P now will be acting at an eccentricity E. So if we draw the cross section here, you can see it. The section is like this. The neutral axis is here, and the pre-stressing tendons are placed over here, and it is having an eccentricity E like this. So what happens is, there is a UDL acting at the top. We will represent this UDL like this. There is a UDL acting at the top. So we will analyze it separately. We will use the linear elastic theory, and we will analyze it separately. This is stresses produced. Okay. So the first one is, due to this P force, there will be a direct stress. That is, I can take it like, if I am drawing it in a single line, there will be the P force like this at an eccentricity E. So which means your basics of your mechanics, I can transfer this P force in equivalent to, I can transfer it like this, that is equivalent to a straight force at its centroid, as well as a P into E moment, that is P and P into E moment. I can transfer it like this. So this concept we will be using, and we will analyze it, or we will do the superpositioning of these two forces, and how we will see how the stresses are being acting. So due to this direct force P, there will be compressive force throughout. This is having section, cross-sectional area A, so that will be a compressive stress plus P by A throughout the section. P by A throughout the section, that is the direct stress will be acting here, direct stress. Then direct stress after that, then due to this P into E, you can imagine like this, but I will draw it separately. First one, due to this compressive force, you have direct stress, that is P by A, that is this beam which is like this will be compressed. It won't go in this shape, but it will be compressed like this. This P by A will be happening like this. The second one, that is due to the bending stress, that is P into E, bending stress due to P into E. You can see here due to this P into E, what is going to happen? This is, you are having the force like this. So imagine that you are keeping a scale like this and you are applying a force with your four fingers at the either end to keeping an eccentricity E like this. So the beam is going to bend in a way that hogging will happen, right? So I can denote it like this. The beam is going to bend in this way. Due to this, it is going to bend like this, and the compression will be at the bottom and tension will be at the top. The compression will be at the bottom and tension will be at the top. This is due to the pre-stressing force and eccentricity. In the last case, there was no eccentricity, that's why we didn't have this bending stress due to this eccentricity. So if I draw the bending stress diagram, it will be, we have the axis like this. Positive we will take it as compression and negative we will take it as tension. So it will be tension at the top and compression at the bottom. So this is compression, this is positive, and this is negative, and I can write it as, you have the basic equation m by I is equal to F by Y. That's why we are writing this. This is the bending stress. This F is the bending stress, so that I can write the bending stress is equal to M into Y by I. That is, here M is here P into E. That is PE into Y by I. This I by Y is your section modulus that I will tell you in the next one. This you can represent this as PE into Y by I here, and this also, this is tensile stress, that is PE into Y by I. Okay, now this is due to the pre-stressing force, so I can represent this like, here the direct stress plus the bending stress, that is bending stress, that is here positive and this is negative, P into E into Y by I, and here P into E into Y by I. Now there is one more remaining, that is your bending caused due to the pre-stressing is over. Now there will be the bending caused due to your applied UDL and self-weight of the structure, right? That is bending stress due to moment created due to the external load. So I can call this as, if I am calling this as capital M, I am calling this as capital M. This load is W kilonewton per meter, and suppose the reaction here is R1 and the reaction here is R2. Then the bending moment diagram will be like this, right? The bending moment diagram will be a parabolic like this, and at any section, if I am taking, suppose this is M suffix X, at any section X, then the bending moment at that section Mx, I can write it as Mx is equal to R1 into X minus W X square by 2. The bending moment at any section, I can write it as here R1 into X minus W X square by 2. That bending moment that is the bending moment due to the applied load and if I am considering the self weight of the structure. So I can write here the third one. It is due to the bending stress due to moment M due to the applied load. So that I can write, due to this applied load, the beam will be deflecting the way you know till the way you have studied before introduction to the pre-stress concrete. So it will be like this. The tension will be at the bottom and compression will be at the top. The neutral axis being like this. So the compression will be here. The compression is over here. This is due to the load which is being applied, W, kilonewton per meter. So if I am drawing the bending stress diagram, I will be getting axis over here. At the top it will be compression, and at the bottom it will be tension, that is negative here, positive here, and that will be the applied moment, that is you have M into Y by I. That M varies according to the section. That's why I have written at the beginning Mx. So here also M into Y by I. Okay, Y being the depth of the neutral axis from the centroid. Sorry, depth of the fiber being considered from the centroid. So the total will be compression like this. So the total bending stress I can write it as, when I am coming here, it will be plus. There's one more thing, that is your compression at the top and tension at the bottom, that is My by I, My by I. So I am representing this compression by total by this red color. Then I can, based on this linear elastic theory, I can superimpose these three stress diagram, that is I can draw it together, and I can write the final stress I'll write here. Final stress at top and final stress at bottom. Final stress at top, I can write it as what? Final stress at top, I can write it as, here the final stress at the top is P by A. We are taking it as positive, plus P by A. This is negative, that is minus P into E into Y by I plus M into Y by I. And at the bottom, that is P by A plus P into Y by I, E into Y by I plus, sorry, minus M into Y by I. So I can write the final stress as, here at the top is plus P by A plus P by A minus P into E into YT divided by I. I'll tell you YT because if it is an unsymmetrical section, the depth of the neutral axis will not be exactly at the center, so the distance between YT and Y bottom will be different. That's why plus, and considering any section, then it is MX into YT divided by I. And if I am considering the final stress at the bottom, then that is again plus P by A plus P into E into Y bottom divided by I minus MX into Y bottom divided by I. Bottom divided by I. So I hope you are clear with this. So if I am drawing the section like this, in order to have a safer section, what is needed? Both should be under compression, that is Y bottom and Y top should be under compression, and we will get the stress like this, that is here I can write it as, this is P by A minus P into E into YT divided by I plus MX into YT divided by I. And here P by A plus P into E into YB divided by I minus MX Y I into YB, and this will be under compression. This will be totally under compressive stress, which means the concrete itself will take all the force which is coming due to the applied load as well as due to the self weight, and the structure will be safe. So now, based on this understanding, Now if you see this, if the tendon is concentric of the cross section, the pre-stressing is simply P by A, which means if it is without any eccentricity, there is only direct force, that is P by A, and this is the case we are not considering the UDL. Let us now discuss the case for an eccentric tendon, that is a simply supported concrete beam subjected to eccentric pre-stressing. That is what we have seen here. The beam section, we have the eccentricity here P, there is no UDL considered, so there will be a direct stress P by A and a bending stress due to this P into E, that is you can see here P into E by ZT. That's what I told. ZT is the section modulus, that is I by Y. Z is equal to I by Y. So here we are representing by section modulus P into E by ZT and ZB, that is section modulus at the top and section modulus at the bottom. The total stress you will get like this, and it will be a compressive stress throughout. So that is we can see here F SUP and F INF. That is another representation which I have said here, that is F top superior and bottom inferior, that is the extreme bottom smaller force and inferior force and top superior force. That's it. And now we will consider the case of a concentrated beam subjected to UDL. You are having a UDL like this. So here let the intensity of the live load be Q, which we have discussed as W, and intensity of the dead load G, which we have discussed as the self height of the structure. The moment due to your live external load, that is MQ, and moment due to gravity load, that is your dead load, is MG. So here we have discussed we will analyze it separately. That is, the first is the direct stress and the second one is the bending stress due to the pre-stressing force. So this two I can club it as the stresses due to the pre-stress, and the next one is due to dead load and live load separately, that is your imposed stresses, and total stress, the resultant stress. So the total stress for the upper and lower, you will get it like this separately. Please do it, find it, write it by yourself. This is the very much basics of your pre-stress. Once you understand this, the rest of the thing is very easy for you. So the net stress at the top and bottom fibers of the concrete can be summarized as this one. Now you can see here the computations are generally based on nominal concrete area, that is we will exclude the area of tendons for all engineering purpose, excluding the important correlation with experiment, because based on the experiment we will see that the tendon area is not considered. Moreover, the changes in loading causes changes in stresses in the concrete only, provided it does not exceed the modulus of rupture of concrete. That's what we have said at the beginning, that we will consider the thing as already it is the tendon is elongated, so that it won't take much. This is in active state, so whatever loading it will change the stress in concrete only. The tendon therefore is assumed to maintain a constant pre-stress. It is always in the active state, providing its ultimate strength. So whatever load is coming, it is taken by the concrete law. So based on this, we will move on to the numericals, and once numericals are done, you will have more clarity on this. So students, thank you. We will see you on the next class.